Okay, welcome to our MA112 online lab class for this week. In this video, I will be discussing our lab exercise for week 12. So let's begin. So this is the lab sheet which we are covering this week. There are a few questions here. Some of these questions are very similar to what we were doing in the previous week. So I think this should be a great practice for all of us. So let's look at question number 1. It says write out the first 20 terms of the sequence, graph these points, and determine whether this sequence converges. Okay, so let's try a few questions from here. Let's look at part 1. In part 1, we're given our sequence is given by n upon 4n minus 1. Our n begins from 1 to positive infinity. Okay, so first of all, let's go ahead and determine our sequence. Let's write our sequence. So an is given by, okay, let me use my basic math assistant. So what do we have? We have n upon 4n minus 1, put a semicolon. Okay, now what I want to do next is I want to create a table, and I'll call that list. So I'll create a table for my sequence values of an, and I'll take my n values from 1 to 20. Okay, we want to find the first 20 terms. Okay, if I go ahead and if I execute this, okay, that we're given our first 20 terms here. So 1/3 is your first term, then 2/7 is your second term, all the way till 20/79, which is your 20th term. Okay, alright, so let's try and plot this. So let's use our list plot function. What do we want to plot? Let's plot our list. Okay, let's use our plot style. Let's use dark blue, and let's just give some value for our point size. Let's say 0.01, and let's just keep our axis origin to be at the point 0, 0. Okay, right, now you can run this. Alright, so it gives us a nice plot here. You can see that your points here, they sort of like flatten out. Over here, as you go towards n equals to 20 in the horizontal axis, you see your curve sort of flattens out. So from the plot, it seems that our sequence here, it converges. Alright, so now also we can determine this by finding the limit. So if we evaluate our limit of our an as n approaches positive infinity, and then just execute this. Alright, we get a value of 1/4. Now, what is the significance of this value 1/4? Well, this tells us that our limit of our sequence as n approaches infinity is 1/4. So our limit is a finite number, a finite value. So this means that our sequence converges. Okay. Alright, let's try another part. Let's try part 3. Okay, let me just format this. Okay, let's see, where is our part 3? Okay, it's over here. So n minus 2 to the power n. Okay, let's just try that out. So let's write our sequence. A n is equal to n minus 2 raised to the power n. Okay, now let's create a list. Let's create a table. So I want to tabulate the values of an, say from 1 to 20. Okay, let's just see what this looks like. Okay, so we get those values there. Let's just do a plot of this. Let's use list plot. I want to plot my list. Plot style. I'll use dark blue as well. And my point size, let me keep it at 0.01. And also my axis origin, let me just keep it at the 0.00. Okay, and then let me just execute this. Okay, so if you look at our graph here, if you look at our plot here, see it sort of flattens initially and then it decreases after 15. From 15 to 20, you see our graph, it continues downwards towards negative infinity. So it doesn't flatten out as you approach infinity, it sort of goes towards negative infinity. So it seems like from this plot here that this sequence here, it diverges. Okay, let's evaluate our limit to verify this. So what do we want to find? We want to find the limit of an as n approaches positive infinity. And then execute this. Alright, okay, so our limit here is negative infinity. This negative infinity tells us that our limit does not exist. So since our limit does not exist, therefore this sequence, it diverges. Okay, great. Okay, let's move to question 2. Let's do some questions from there. It says determine whether the series converges, and if so, find its sum. Okay, and plot the partial sums. Okay, let's do let me just go up here. Let's do part 1. Let's do part A. Okay, so we're given our series here, 1 upon 2k plus 1. Okay, so let's first of all write down our sequence. Sorry, our series is given by AK 1 upon, okay, let me use my fraction, 1 upon 2k plus 1. Okay, so let's use our sum convergence. Okay, this sum convergence will tell us whether the series converges or diverges. Yeah? If the sum convergence is true, then the series converges. If the sum convergence is false, then the series diverges. Okay, so let's just run this. Let's execute this. Okay, so our output here is false. So this means that the series is divergent for part A. Okay, let's try part B. Okay. So part B, we're given this series here. So let's just write down our AK. So AK is given by, let me use a fraction. In my numerator, I have the square root of K. In my denominator, I have K to the power 3 plus 1. Okay, again, let's evaluate our sum convergence. And then let's see whether this series converges or whether it diverges. So let's just execute this. Okay, our output is true. So that means that this series is convergent. Okay, so the question tells us determine whether the series converges, and if so, find its sum and plot the partial sums. Okay, so we can do that for part B since this series converges. Okay, so let's just find our sum. Okay, the sum of AK K from 1 to positive infinity. And let me just execute this. Okay, great. So we do get a value. The reason why I have put a capital N in front here is so that I can get a numerical value of the sum. Okay, let's do a plot. Let's do a discrete plot. We want to plot the sum. Sum of AK K from 1 to N. N to 25. Plot range. Let's take all, and axis origin. Again, let's keep it at 0, 0. And then execute this. Okay, excellent. So again, if you can see this plot here, it also tells us that this series here is convergent. Okay, let's move to question 3. Okay, let's look at part A. Okay, let me just type this out. Okay, now what we see here is, if we try to list out the first few terms of this series here, it'll begin with substituting k equals to 1. Now in a numerator, we'll have cos of 1 times pi, which is just pi. So cos of pi is negative 1. So that means our first term will be negative 1 upon 1, which comes to negative 1. Now next value of k will be 2. So 2 times pi will be 2 pi. Cos of 2 pi is positive 1. So you'll have positive 1 upon 2. So this will be plus half. And then you substitute 3. So cos 3 pi will become negative 1. So you'll have negative 1 upon 3. So that will be negative 1/3. Okay. And then you can sort of pick up a pattern here that you end up having some alternating series. Okay. Now, if I express this as an alternating series, this here is same as my numerator. It can be very simply be negative 1 raised to the power k. So you have negative 1 to the power k upon k. So this is the resulting alternating series that we get. Okay, so the question asks us, classify each series absolutely convergent, conditionally convergent, or divergent. Okay, so we are looking at part A now. Okay, so let's check for absolute convergence. Okay, so for absolute convergence, right, we have a problem here. Let me just remove these ones here. So what we need to do here is we need to take the absolute value of this. Okay, so we need to take the absolute value of that. So therefore we have to take the absolute value of this as well. Okay, so if you take the absolute value of this, so that negative 1 to the power k, the resulting value will always be a positive 1. So therefore this here is same as having just positive 1 to the power k, and then 1 to the power k, well, basically it will still remain 1. So it just simplifies to give 1 over k. Okay, so now we'll use this 1 over k to check for absolute convergence. Okay, so our ak is equal to 1 over k. So let's just write that. Okay, so let us check for sum convergence. So the sum convergence of AK, again, if it's true, it converges. If it's false, it diverges. False. Okay, well, I'm checking here for absolute convergence. So this output of false here, it tells me that this series here, it is not absolutely convergent. Okay, so since that's the case, I will need to check for convergence. I need to check for convergence now. Okay, so let me create, say, my BK. So BK, I will just take my initial problem, which is cos k times pi upon k. Okay, and then let's use our sum convergence. Okay, all right. So our sum convergence is true. So what does that mean? That means that our series, it converges. So let me just write a conclusion here. Okay, so what does this mean? This means that, okay, so how do you approach this type of questions? Well, initially, the first thing you need to do is you need to check for absolute convergence. Okay, so if the sequence converges absolutely, then you can conclude that the series converges directly. Yeah, you can make that conclusion. Okay, however, when we did for this question, when we check for absolute convergence, it did not, it was not um, absolutely convergent. So in that case, we have to move to the next step, which is to check for convergence. And when we checked for convergence, we found out that the series is in fact convergent. So therefore, what we can conclude is that this series here is conditionally convergent. Okay, let's try another part. Okay, let's try part D. Okay, let me just copy this here. So now I'm going to do part D. So we have raised to the power k. Okay, so this one here, okay, there is a negative in front of this. Okay, great. So we have a negative 1 upon ln k, whole thing raised to the power k. Okay, so if we apply our properties of exponents here, I raise my numerator to that power k, I raise my denominator ln k to that power k, and then if I do that, my problem simplifies to become, I'll have that negative 1 will become raised to the power k, and in my denominator, yeah, so your ln k will also be raised to the power k. Okay, great. So first thing we must always do, we need to check for absolute convergence. Check for absolute convergence. Okay, so again, what we're going to do is we take the absolute value of this. So we're given this, so what we need to do is we need to take the absolute value of all of that. Right, so similarly, we need to take the absolute value of this. Now if you do that, then this problem here, it simplifies to become, instead of negative 1 to the power k, you'll become the you'll take the absolute value of that, so your numerator will just simplify to become positive 1. So you have 1 upon ln k to the power k. Okay, so we'll use this part here to check for absolute convergence. So let's create our series is given by ak equals to 1 upon, okay, ln, okay, for ln I need to use natural logarithm, so I'll use this one here, log k. Alright, and then this here, it needs to be raised to the power k. Okay, right, great. So that's what we have there. Now let's check for sum convergence. So if I check for my sum convergence of AK, again for this one, if it's true, it converges. If it's false, diverges. Okay, well, let's check this again. Okay. Okay, right. So for this one here, part D, we checked for our absolute convergence and we found that it is true. What does this true mean? It means that it is absolutely convergent. Okay, so let me just write a conclusion here. Okay, conclusion. Hence the series converges absolutely and therefore it converges. Right, great. Okay, so we've gone through 2 problems from the question 3. You can try out the other parts as well for your practice. Also, if you have any queries, any questions on any of these methods, please make use of the discussion forum. Post your questions in the discussion forum on Moodle. The teaching team are ready to help you and assist you in any way that we can. So please keep in touch and keep safe, and I wish you all the very best in your studies this week. Thank you very much.